In today's video, we are going to explore how graphs can be used to measure both the mean rate of a chemical reaction and the rate at a specific point in time. Previously, we learned that the rate of a chemical reaction can be calculated by dividing either the amount of reactants that have been consumed or the amount of products that have been formed by the time it took for that change to happen. For example, if a reaction between magnesium and hydrochloric acid produced 1,200 cubic centimeters of hydrogen gas in 4 minutes, then to calculate the mean rate, we would divide 1,200 by 4 times 60 seconds, which is 240 seconds, giving us a mean rate of 5 cubic centimeters per second. However, the limitation of this calculation is that it only provides an average rate across the entire 4-minute period. In reality, chemical reactions typically proceed faster at the beginning when more reactant particles are available, and then slow down as the reactants are gradually used up. In fact, by the 4th minute, the reaction may have completely finished. If we could monitor how much gas is being produced at different moments during the reaction, we could plot that information on a graph to visually observe how the rate of reaction changes over time. In such a graph, time would be shown on the horizontal axis, and the volume of hydrogen gas produced on the vertical axis. At the start of the reaction, there are large amounts of magnesium and acid present, so hydrogen gas is produced rapidly. This results in a steep curve, indicating a high reaction rate. As the magnesium gets consumed, the reaction slows down and less hydrogen is produced, causing the graph to become less steep. Eventually, the curve flattens out, or plateaus, indicating that no more hydrogen is being formed because all the magnesium has been used up. When presented with a graph like this, there are 2 common tasks you may be asked to perform. The first is calculating the mean rate of the reaction over a specific time period, which we have already done earlier. For instance, if you are asked to find the mean rate of reaction during the first 3 minutes, you would start by locating the 3-minute mark on the time axis. From that point, draw a vertical dashed line upward until it meets the curve. Then, draw a horizontal line from that intersection across to the vertical axis to determine the volume of hydrogen gas produced in those 3 minutes. If this value is 1,200 cubic centimeters, then you divide that by 180 seconds to find the average rate, which is approximately 6.67 cubic centimeters per second. The second common task is to calculate the rate of reaction at a particular time, which is different from the mean. This involves finding the instantaneous rate at a specific moment using the gradient of the curve at that point. For example, to determine the rate at exactly 2 minutes, start by finding the 2-minute mark on the time axis and follow it upward to the curve. At that point, instead of drawing a line across to the vertical axis, you need to draw a tangent, a straight line that just touches the curve at that exact spot and has the same slope or gradient as the curve at that point. Once the tangent is drawn, extend it long enough to reach both the x-axis and y-axis to maximize accuracy. From one end of the tangent, draw a vertical and a horizontal line to form a right triangle. Measure the vertical change in hydrogen volume, known as delta Y, and the horizontal change in time, known as delta X. In this example, suppose delta Y is 600 cubic centimeters and delta X is 170 seconds. Dividing 600 by 170 gives a rate of approximately 3.53 cubic centimeters per second. If you are worried about drawing the tangent perfectly, remember that examiners understand you are estimating by eye. As long as your tangent matches the steepness of the curve at that point, your answer will be accepted within a reasonable margin of error. Before we finish, it is worth noting that the same method can be applied to a different type of graph, such as one that shows the mass of magnesium remaining over time. In this type of graph, the vertical axis shows mass, and the curve begins at the initial mass, say 1.2 grams, and declines quickly at first, then slows down over time. If you were asked to find the rate of reaction at 1 minute, you would again draw a tangent at that 1-minute mark, estimate the change in mass and change in time, and calculate the rate. For example, if the mass changes by 0.72 grams over 100 seconds, the rate would be 0.0072 grams per second. Even if your values differ slightly, depending on how you draw the tangent, your answer is still valid as long as the tangent is accurate in terms of its slope. The goal is to match the gradient at that specific point on the curve. That concludes our discussion for today. If you found this helpful, please like and subscribe, and we will see you in the next video.